Good evening, everybody, and welcome to the second Marine Evening for 2024. Can everybody hear me okay? Alright, I also want to say a special thank you to our online viewers tuning in tonight. We're also streaming on YouTube. You guys don't have to worry. Unless you want to be on YouTube, then you can come to the front afterwards. Alright, guys, I heard the first night was a success. So everybody that joined last month, thanks again for being here. And for those who have not been here in a while, have you noticed the upgrades? I mean, it's a different place these days. So I hope you guys enjoy your evening. I'm going to introduce someone that's probably not a stranger to you guys at all. Our friendly Kos Coronaios, who will be speaking tonight on a very cool subject, the speed of light. Just a short introduction for Kos. He has been a dedicated member of the Southern African Astronomy Society, as well as the founder and the chair of the Southern Cape Astronomy Club. So let's put a warm welcome together for Kos.
Thanks, Kerry. Sorry, I'm not used to mics. Let me just get the distance sorted out first. Is that okay? Everybody can hear me, I suppose. Thanks for being here. I hope you are going to enjoy it as much as I enjoy talking about astronomy. Speed of light is a reasonably new subject for me, but we'll give it a bash. So when we head out in the evening sky and we look up at the stars with our naked eye, we can generally see about 3,000 stars with our naked eye. With a small telescope, we can see around about 600,000 stars. And the interesting thing, apart from one or two objects that, maybe a handful of objects that are visible with our naked eye, most of the stuff, most of the nebula, most of the stars, most of the galaxies, well, not galaxies, but all the little fuzzballs, the little fuzzies, the open clusters, are all part of our Milky Way. So there's a picture there. Those two clouds there are two galaxies, two regular galaxies. But all those stars there, all that nebulosity that you see, it's all part of our Milky Way. And as we all know, that's our galaxy, 100,000 light years across. The light taking 100,000 years to go from one end to the other. When we look up at the sky, especially with telescopes, large enough telescopes, or even small amateur telescopes, we're looking back in time. It's actually quite interesting to, even with the naked eye, to be able to see Andromeda Galaxy, which is a couple of million light years away, and you can see that from Pearly or Kansbah with your naked eye. So you're actually looking back at the past, which is actually quite cool. Yeah, this is slightly different for me, and normally I'm used to sitting that side. It's the first time I'm actually doing a presentation on the Marine Evening. But it's Wilfred. Wilfred, where are you? It's your fault. He asked me, and I said to him, yes, I would do a presentation, but on a subject that I'm more familiar with, like, I don't know, comets, observing comets, or meteor showers, or just astrophotography. But he was adamant. He wanted me to do a presentation on the speed of light. And I said, no, not prepared to. Anyway, here I am. All right, but this is, of course, going to be an astronomy-related evening. And you might ask yourselves, what has a marine evening got to do with either astronomy or the speed of light? Well, quite a lot, actually. Both subjects have got a lot of science associated with it, lots of collecting data, analyzing data, observing and recording certain patterns, experimenting, and much, much more, as our resident marine biologists will attest. I also know there's a few amateur astronomers in the crowd, which is quite nice to see, so they will also agree with that. But let's just stick with this experimenting for a second. The ancient Greeks were pretty good at experimenting and building on the knowledge of the Egyptians. They got a lot of science right back then. They also got a lot wrong, but they realized early on that the Earth was not flat, but a curved sphere. And Alexander, a Greek philosopher around about 540 BC, who was sometimes called the father of astronomy, deduced by observing Polaris, the northern star, from different latitudes that the Earth could not possibly be flat, which is quite interesting because we still have flat Earthers around that believe that the Earth is flat. So we can go back 500 years and realize that that's not the case. As I said, they got a lot wrong as well. That they did think that the Earth was the center of the solar system, of the universe, that everything revolved around us, and that we were stationary, of course. And around 300 BC, Aristotle was the one that actually still thought that we were the center of the universe. We now know, of course, that that's totally wrong. Nicholas Copernicus, some 2,200 years later, basically it gave us a sun-centered solar system. Sorry, Ma. That's better. And then we get to another Greek. His name is Eratosthenes. He lived around about 270, 280 BC. And he was often called Beta by his contemporaries, because apparently he was second best at everything. But it's actually pretty clear that Beta, or Eratosthenes, wasn't. He was an astronomer, a historian, a geographer, a philosopher, a poet, a theatre critic, and a mathematician. And he was at the top of his game. He was really, really alpha. And he was also at some point in his youth, the director of the library in Alexandria. One day, while reading the papyrus book, he came across a very curious account. In the southernmost frontier of Sin, near the first cataract of the river Nile, at noon on the longest day of the year, vertical sticks cast no shadows. Vertical sticks cast no shadows, and the columns grew shorter and shorter, and at noon they were gone. A reflection of the sun could be seen at the bottom of the wells. The sun was directly overhead. It was an observation that someone might easily have ignored. Stick shadows, reflections in wells, the position of the sun. What importance could that have in everyday matters? But Aristophanes was a scientist, and his thinking on this changed the world. In actual fact, probably made the world. So he asked himself, how could a stick in Seine cast no shadow, and a stick in Alexandria, there we go, cast a substantial shadow? So consider two vertical sticks in Seine and one in Alexandria. Suppose at a certain moment each stick casts no shadow at all. This would be perfectly easy to understand in a flat Earth. If the sticks cast shadow of equal lengths, that would also be quite easy to understand if you believe in the first flat Earth scenario. But how can it be that at the same instant there is no shadow in Seine and a substantial shadow in Alexandria? The only possible answer is that the Earth is curved. Not only that, but the greater the curvature, the greater the difference in shadow lengths. So all it took was a little bit of experimenting, a slave to walk the distance between the two towns or the two cities, and he could quite easily work out how big the Earth was, or what the circumference of the Earth was. 7 degrees is about 1/50th of 360, which is a circle, and just using simple geometry, he figured out that the Earth was around 10,000 kilometers 10,000 kilometers in circumference, which is close. It's about 5% close, and that was back then. So it's quite interesting that back then we knew the size of the Earth. It is also quite strange that the explorer and mariner Christopher Columbus basically got his calculations wrong when he thought that he had circumnavigated the Earth. Of course, we know that he didn't, and he found Americas, and it was actually Magellan who got that right. So let's get back to the speed of light in our own backyard. If you saw that initial, I'm just going to go back. Sorry. Oops. We'll get to it. Okay, so the Earth's circumference is about 40,000 kilometers around the equator. In 1 second, light travels 7.5 times around the Earth. So 1 second, 7.5 times. That's pretty fast. In Afrikaans we say, "Here, dis vinnig." Now I'm just going to add some zeros up there so we can just refresh our memories with how many zeros in a million, in 1 billion, in 1 trillion. I don't want to mess it up like Zuma. So that's just... and then of course after that we're going to end up putting powers to the 10, okay? Because then the figures get hugely astronomical, and you can't talk about trillions, etc., etc. It's just too much. All right, so from our solar system, there we go. That's the one I was looking at. Okay, so there's the speed of light: 299,792,458 meters per second. Okay, we're going to narrow that down. We're not going to mess around, and so we're just going to call it either 300,000 kilometers per second or 186,000 miles per second. Let's just use those two figures. Much easier to say. So that's the speed of light. And that's just a graphic showing 7.5 times. Okay, so from our star, from the sun, the first planet that it hits is Mercury. The planet spins so fast, so slowly around its axis, that sunrise to sunset is about 180 Earth days. Okay, and it takes about 3.5 minutes for sunlight to hit the surface. Next up, we've got Venus. After 6 minutes, nearly double the time, it reaches the hottest planet of our solar system, which is such a strange world. It experiences all its seasons in 1 day. It basically takes 1 day to revolve around its axis, and the same time as to complete an orbit around the sun. So you have all the seasons in 1 day. But also, interestingly enough, is the only planet that moves in retrograde motion, or orbits, not orbits, but it moves on its axis in retrograde motion. So you have the sun rising in the west as opposed to the east. Very inhospitable planet. Sunlight takes about 6.5 minutes to get there. Okay, then next up, sorry, I missed Venus. And it's one of the few planets that we can actually see absolutely no detail on. As you can see from the picture that was taken by Angus Burns from Newcastle, the planet is shrouded in clouds, so we can never actually see the surface. Next up, the pale blue dot, as Carl Sagan described it. When Voyager 1 zoomed past Saturn, it turned around, it turned its cameras around, and it took a picture of the rings with the Earth in the background. It was about 2 billion kilometers away, and that's our planet there. So from the sun to the Earth, light takes anything from 8 to 8.5 minutes to reach us. So to have a look at that, that's quite a profound picture from that spacecraft. And of course, Carl Sagan, one of my favorites. If you've read any of his books, you'll know why. And if you haven't, please read them. They really, really are worth reading. From the Earth, we hit Mars. Again, this image is by Angus Burns from Newcastle. That's what Mars looks like through not through a telescope, but when it's been imaged and stacked, but through a telescope. And the big thing here is that you notice is the polar cap as it grows and diminishes over time. And on Mars, Curiosity is still doing its thing, and it's also unfortunately the next planet we're going to mess up. I reckon by the time this decade is over, we'll be very, very close to getting to Mars. From Mars, we move through the asteroid belt and we get to one of the giant gas planets, Jupiter, with its 95 odd moons, 4 of which were discovered by Galileo. And it's about 590, 600 million kilometers from us. The light reaching Jupiter takes about 45 minutes. If you're, again, a picture from Angus Burns. If you took, we did the North-South gas plan last week, so if your mate was on Mars and wanted to find out what the score was, radio waves travel as fast as light waves, so 45 minutes. If you phoned you to find out what the score was, by the time you received that message, phoned him back, the Bulls would have already won. Game over. Sorry, Province supporters. And then we reach Saturn with its spectacular ring system. The planet isn't just bathed by sunlight, it's also bathed by ring lights. So all the rings are little chunks of ice, some as small as marbles, with different facets. And that's what we're looking at, it's basically just chunks of ice. Light takes about 80 minutes to get there. The planet sits about 1.2 billion kilometers from us. And then from Saturn, we move past the 2 gas giants and we head out towards Uranus and Neptune. And I've just got a graphic there. So there's the inner solar system with Jupiter. There's the orbit of Jupiter. Saturn's just outside there. And on the graphic on the right hand side, you see the orbit of Saturn with the Kuiper belt. So past Jupiter, past Saturn, we head out towards Pluto, which is that purple orbit there. We head out past Pluto towards dwarf planet Sedna, which is out there. That's to scale, by the way, past the Kuiper belt. And that's where things start taking much longer. Light from Sedna would take, well, first of all, if you had to look back at the sun, it would just be another star in the sky. You wouldn't be able to see a disk, you wouldn't be able to see too much sunlight, and light would take at least close to 2 hours to reach Sedna. Beyond Sedna is a cocktail of extremely dilute gas, mostly hydrogen and helium, that's left over from the Big Bang. That's just a graphic representation of what the scientists think Sedna looks like. And from here you can see that's the orbit of Sedna. So that inner solar system with the rest of the planets is squashed in a little square there. And there's the orbit of Sedna. Every now, so we get to the Oort cloud. It's about 200,000 AUs. I'll talk about AUs now. From us, the Oort cloud lies about 300 trillion kilometers from the sun. And this is where we're going to change our units. We'll talk about the astronomical unit, which is basically one AU is the distance from the sun to the Earth, which is roughly about 150 million kilometers. The Oort cloud sits 200,000 AUs, so it's pretty far. The light there takes over 3 hours to get to. 3 hours. It's not even to our closest star yet, or the closest star to our star. And out where the Oort cloud is, our sun still plays a major role. Its gravitational attraction is still, although it's weak, it's still strong enough to pull in comets and asteroids that basically bring them in towards the sun, and then round for more orbits depending on the asteroid or the comet. Some of them come back over years of time, 70 years, 100 years, 200 years, and some leave the solar system and never come back. And that's basically the extent of our solar system, and the influence that the sun has. After the Oort cloud, the light that escapes will take over 4 years, just over 4 years, to reach the closest star to the sun, and that is called Proxima Centauri. It's a red dwarf, a star among 200 billion ones that make up the Milky Way. So in terms of the speed of light, what does it all mean? Okay, so as one of the most fundamental constants in nature, the speed of light is the ultimate speed limit at which all information and particles can travel. That includes photons and radio waves. As you see there, I've got some quick facts. We've covered how many times around the Earth, how long it takes to go around, how long it takes to get from the sun to the Earth. Light can be reflected, absorbed, or transmitted. Light waves can certainly interfere with each other, and they can behave as particles do. Or waves, both wave-like and particle-like properties. So who discovered the speed of light? The first name I've put there in 1676 is Euler Romer. He was basically trying to time occultations of one of Jupiter's moons, Io, and trying to predict when we would re-see an occultation. So he wasn't even trying to determine the speed of light. He basically just stumbled upon it by pure fluke. What happened was he was taking measurements from the Earth at different times around the sun, and that value was different because of the distances associated with it. It's actually quite interesting that in the sort of same age, René Descartes, the French scientist and philosopher, believed that the speed of light had an infinite speed. And Romer actually, well, he didn't explain, but he showed that it didn't. So it just shows you, over the years, the different methods of finding those speeds, and eventually the adopted value of what we use now. So how do we measure it? We use techniques like timing light's travel between 2 points, observing astronomical phenomena. When we look at eclipses, be they solar eclipses or eclipses of asteroids by stars or stars by asteroids, we can certainly measure the speed of light. We can conduct experiments and use high precision instruments. But why is it so important? Why is the speed of light so important, especially to astronomy and to science? It's very crucial in understanding the fundamental workings of the universe. Without that value, a lot of things don't come into play. A lot of basic science does not come into play. It plays a vital role in theories, in relativity, in quantum mechanics, and has practical implications in our telecommunications. All the Starlink satellites, which don't get me going on Starlink. Basically, if it wasn't for those formulas that we use for determining speed of light or the value for the speed of light, it would be very difficult for us to put those satellites into orbit and keep a good time, check on what they're doing, where they are, etc., etc. The interesting bit now comes with, so light's been traveling for a year, we refer to it as a light year, and if you do the maths, you've got your value of 186,000 miles per second. You multiply that by 60, from seconds to minutes, another 60 to get to hours, 24, etc., etc. And you get to, come on guys, what's the figure? I showed you all those zeros earlier on. 5,000, I've written it down. I'm not going to mess it up like zoom in. 5,855 billion miles in one year. That's far. We're going to just change that and just talk about 6 million miles or 9.6 trillion kilometers. That's in 1 year. So when we talk about the speed of light traveling across our Milky Way from one end to the other, and it's 100,000 light years. Multiply that by 100,000, you get a lot of zeros. I'll show you just now. Okay, so that unit of length, the distance light travels in 1 year, it's not speed. The unit of length is actually, it measures distances, enormous distances. There's another unit that we use over and above this, it's called a parsec, which is equal to 3.2 light years. But I'll cover that just now. So how big is our galaxy? We've said it's 100,000 kilometers across. And we measured it in light years. And we can get a rough idea of how far we've traveled. It's just an artist's impression of our Milky Way. The center of the galaxy is over there. We sit on a spur called the round spur, about 30,000 light years from the center. And as we spoke about, that distance that spans across there is 100,000 light years. We actually see the brightest part of our galaxy in winter. It's coming up now with Orion rising. I think it clears the horizon at about 10, 11 o'clock at night. So we should be getting some nice, depending on the weather, some nice views of the Milky Way. And of course, the dimmest part of the Milky Way is during summer, around Orion, where we see the outer arms of our galaxy. That's just another picture from the observatory in winter with the Milky Way pretty much overhead. I had the camera at the bottom of on the floor looking up at the tripod. That figure there is the distance if you look at light traveling across our Milky Way, 100,000 light years. If you do the multiplication, you come out with 9,400 billion trillion kilometers. Pretty far. Okay, and that just gives us an idea of, at the moment, of the speeds that we can travel. Okay, so most of our satellites travel around about between 50 and 70 kilometers per second. So it's taken Voyager 6 years to get to Jupiter. At those speeds, okay, it would take over 40,000 years to get to Proxima Centauri. At car speeds, 48 million years. At jumbo jet speeds, 2 million years. A drive to the sun at 120 kilometers would take us 142 years. And I mean, the sun's just around the corner. It's 8.5 minutes light, 8.5 light minutes away. To Sedna on the outer, well, not the outer, but out in our solar system, 1,700 years. So we're talking about vast time here. By the time Voyager reaches the Oort cloud and comes out on the other side, we're looking at 25,000 years. We'll talk about wormholes just now, or not. I thought I'd just add that in. It was just a nice picture I grabbed from Google of a space shuttle traveling towards a donut-shaped wormhole. We'll chat about that just now. Okay, but we can't talk about speed of light and the mass and the science associated with it without mentioning two very, very, very important giants that basically Einstein stood on their shoulders, not on. Of course, Newton and Maxwell. Newton gave us his laws of motion. His laws are basically universal across the whole of the universe. They still apply. They apply on Earth. They apply out there. The only issue with Newton's laws is that you always have to have a little phrase that's associated with Newton, and that those velocities of his are, although they're universal, you have to have, with respect, accompany whatever you are doing in terms of motion. So if you look at this diagram now, and we see a train traveling at 40 kilometers an hour, with respect to with another train moving at 20 kilometers an hour. So the difference is basically 20 kilometers an hour. If you had a train traveling at 60 the other way, the figures, the values would change to 40 kilometers an hour if you were moving, that way. So it's always with respect to another object. It's never just on your own. And with Newton, you can add velocities on a moving platform. You can add or subtract velocities. You'll see how that changes just now. And then we have Maxwell's laws of electromagnetism. His main law was that electromagnetic waves travel, such as light travel, are constant in terms of speed, regardless of who you are, where you are, and what you are doing. So that speed of that wave is always constant. That was his big thing. So it doesn't matter whether you're stationary on a spaceship. The speed of light is constant. So if you think about it, if you think of Newtonian laws, and you think about this constant speed of light value, it doesn't quite gel, does it? How can you have universal laws where you can add velocities with a moving platform, and then you have a constant speed of light? So for argument's sake, if we were, sorry, I'm missing a graphic there. I'll get back to that. So if we're sitting here stationary, our relative speeds are zero, correct? If we had to all get onto a train, and the train was moving at 75 miles per hour, our speed would then be 75 miles per hour, correct? To everybody on the train. Somebody outside the train would see it differently. But if we carried on moving, we moved around the sun and around the galaxy, and you added those speeds like you were able to, you'd see that we actually, our speed would be 581,075 miles per hour. That excludes the fact that our galaxy is also moving. But if we're all moving in the same direction, so that vector is the same, that would be our speed. So I'm just going to go back. So Einstein's problem, or his big dilemma, was how can you, if the speed of light is constant, what happens when you're moving? So this is the interesting part. So a man is standing on the platform over here at sea, and two lightning strikes happen simultaneously at the same time, and he's standing in the middle of that platform. He sees those two strikes happen simultaneously. There's no strike happening before or after. It's always at the same time. Someone on the train traveling at the speed of light sees it differently. If the speed of light confirms what Einstein was saying about relativity, that the person on the train can't see those two stars simultaneously. He will see one first and then the other one. Does that make sense? So he's traveling towards one, he would see that one first, the one behind him, not because he can't, would happen slightly later. So he had a difficult choice, Einstein. Either Newton's laws were not universal, or the speed of light was not constant. So he had to think about something, he had to work out and theorize, if the speed of light is constant, what do we do to actually change that value? Because the two observers will see two different values of the speed of light, but they can't. They have to have the same value. So what do we do? So he came up with time dilation. In a nutshell, basically, the person on the train, time slows down. So by slowing down, those two values become the same. You can get that value down to the constant value that the person on the platform could see. So I'll explain a little bit later about that as well. And of course, he called this theory special relativity. Oops. Dinosaurs. Okay, so according to Einstein, you can manipulate. Let's just recap there. So of course, time. Time doesn't really care about us. It moves on. It ticks away. You can use it when you have it, but you can't keep it. You can't store it away. It's always moving forward. We live through minutes, hours, 24 hours in a day, months, a year later, and time just moves on. That's what we know, correct? Nope. Slightly different. According to Einstein, you can manipulate time if you try hard enough. This is the part that I quite like. So we evolved in a sort of medium environment. We're not small stuff like electrons and atoms and quarks and the like. We are not large like planets and stars and supermassive black holes. We're sort of middle of the road, and we also operate at medium speeds. We're not as slow as snails or tectonic plates, and we're certainly not as fast as the speed of light. But physics operates in a pretty predictable way, and the world that we inhabit is pretty normal. So what is the difference here with time and speed and the speed of light? Newtonian laws apply and are universal. When we look at solar eclipses, and when we plan ahead, we can work out solar eclipses, when they're going to happen, when is this comet going to come past around the sun, and we can get a good look at it, etc., etc., etc. So time ticks forward and in one direction at a consistent rate, and all according to plan. We can work out lots of things that are going to happen in our solar system, in the universe. But outside our medium-sized world, things get a bit weird. When we start slowing things down, when we start moving much faster, things do get weird. So physics breaks down when we get too small or too massive. Gravity does things that we can't quite work out. Quantum effects take place and they find their way in. Things just cease to play by the rules as we know them. Special relativity concluded that the speed of light is consistent for all observers. Photons moving through the vacuum travel at a staggering 186 miles per second, regardless of anything, regardless of who you are, what you are. That speed is very impressive, as we've seen. It's fast enough that the time delay between when light hits an object and when we notice it is very, very short, which is pretty good, especially for our ancient ancestors it would have been difficult to evade predators if we were already horse swallowed by the time we noticed them. Casing for it. The speed of light, though, becomes even more impressive and bizarre because of the way it remains constant no matter what the position or speed of the observer. So let's just break that down. That was the one I was. We'll break that down just now. This graphic just basically shows you time here ticking away. You've got a mirror there, and we're standing still. And your second is just going up and down, and there's your time ticking away. This one here, slightly different. It's actually on a moving platform, and that length of tick, much more greater distance because of your movement, your vector going that way. And it takes much longer to do one tick as opposed to up and down. So as we mentioned with Newtonian laws, speeds compound, but Einstein basically said we'd have to slow time down to be able to get that value constant and the same. So if we had to replace that traveller on the train with the speed of light, things change drastically. Although the speed of light remains the same, special relativity suggests a counterintuitive solution to Einstein's problem, which is basically slowing time down. So changing the length of each tick on the clock allows the speed of light to remain consistent no matter how fast you're traveling in respect to it. I don't know if you are reading through that, but two very important aspects to Einstein's special relativity is that the one is that the same laws of physics apply equally in all constant moving frames. So it doesn't matter whether you're stationary, moving, or what you're doing, that reference frame is still a correct reference frame for yourself. So again, an observer on a train sees time ticking away nice and slowly. If you throw a ball up in the air, the ball will just go up and come back down. An observer at the station would see the ball basically moving through the air in an arc. And then that second point was, regardless, we can't use Newtonian velocities and laws, regardless of how fast you're traveling. If you shine a torch or if there's a light that you're carrying, that speed of light is constant and you can't add velocities. You can't combine those speeds. And in a nutshell, basically, that is his theory of relativity. I'm just going to go back. So these Einstein's theory of relativity were basically just theories and workings out. All basically everything that we've discussed so far, that we've covered so far, can all be surmised with maths. That's how he figured it out initially, and thinking upon it. So we can do all these theories with maths, but they are now, as we know, they have been confirmed by observations and experimentations. So this time dilation we actually utilize on satellites because they're orbiting at speeds much faster than we are on the ground. A satellite's internal clock will run much more slowly. The difference is not very big because it's not traveling at much higher, at high speeds, but it's traveling faster than what we do. So there is a difference, and over time it does stack up. What throws a spanner in the works is gravity. So over and above the speed and the distance from an object, we also have now gravity that's plays a very big role. So gravity bends space-time, and since GPS satellites orbit so far away from the surface of the Earth, they feel the effects of gravity much less. It makes logic much less than what we do. So it causes the clocks to tick much more quickly. So GPS satellites drift by about 38 microseconds into the future every day, if we didn't account for relativity. And they do actually have to set a counter relativity for those GPS satellites, especially for aircraft. It would play havoc with your GPS signals. The very interesting thing here is that those satellites are actually time traveling at a rate of 1 second every 72 years. It's a very, very small rate because they're very slow in comparison to the speed of light, but they are actually time traveling at about 70 to 80 years. That's just a graphic showing you the different clocks and scenarios of satellites and gravity and speeds. And of course, this is the famous equation that we're all familiar with. Robin, you should know this. Don't worry about the joules. I'll explain that later. I'll come back to the slide. So basically, Einstein's theory of relativity and his general theory can be surmised in one equation, and on a very basic level, what it says that mass is interchangeable with energy. The only thing constant there is the speed of light. So we know how much that is, 186,000 miles per second, if you've been paying attention. How much in kilometers? Good stuff. Okay, and then that figure there is, if you had to take 1 kilogram and do the equation of how much energy is measured in joules, what sort of energy are you looking at? So 90, it's 9 with how many zeros? Forget about it. That amount of energy could power South Africans' electricity for a couple of years, and that's just 1 kilogram of mass. Okay? That's how much energy you would get at that speed of light squared. So that figure there is the biggie. Okay. So yeah, mix these up. I don't know why. Okay, the interesting thing here is that regarding the speed of light is that as soon as you start moving close to that speed, that 186,000 miles per second, with that equation there, you can actually see that its mass rises greatly. The mass actually is huge. The energy requiring to move that mass also becomes infinite. So as you get closer and closer to the speed of light, both those numbers, the energy value and the mass value, go sky high. So basically for that reason, there's nothing that we know that can travel at the speed of light. It would require too much energy, and the mass would be too huge. It'd be like rolling a ball up a hill, and the hill's getting steeper and steeper and steeper, and the closer you get to the top, the more difficult it is to get that ball up to the top, or that rock up to the top. It becomes insurmountable. There's just another graphic showing you how an observer on the ground sees that time dilation moving, and how an observer in a space rocket sees that time ticking away. It's it's normal. And there's just an explanation on time dilation. So one takes into account special relativity, and then, as I mentioned earlier, general relativity, gravity also plays a huge role. So Einstein realized that with varying velocities, gravity is also an issue, and he basically claimed that gravity, time, and space were one and the same. And they form a four-dimensional fabric called space-time. And this is where we start thinking about traveling, and it becomes a little bit more doable, but you'll see it actually doesn't. So this version of, not Einstein, but this version of space-time is like having a bowling ball and then a smaller ball, and how it changes the fabric of space around it that we can't see. We can't visualize that, whereas that's a good way of showing how it works. Of course, that small ball will move towards the bigger ball, go down, pick up speed, and then swing around. Just a quick speeds of what we've accomplished. So Chuck Yeager broke the sound barrier in 1947. That's the fastest we've ever been. That was quite a long time ago. Notwithstanding the fact that the speed of sound was an engineering problem. So that was quite easy to overcome. It was an engineering problem. It wasn't a speed of light, a universal issue. Apollo 11, 25,000 miles per hour. But look at that percentage, it's 0.0037% of the speed of light. We haven't even hit 1% yet. The Parker Solar Probe, launched in 2018, was reasonably quick, but it's still, we need to move 15 times faster to hit 1% of the speed of light, just 1%. But then we see what happens when we do get close to those, to that 100%. 90% of the speed of light for 10 years, and 23 years have passed on Earth at those speeds. If you go to 99.99 for 1 year, more than 2,000 years would have passed on Earth. So that's a time dilation thing. At those speeds, those very fast speeds, time just about slows down. Those seconds take years to tick, whereas on Earth, everything happens normally. You just carry on, time just carries on moving, going forward. You go to, as I said, 99.99%, 2,000 years would have passed on Earth. At that speed, to our closest star, it would take 4 years to get there. Alpha Centauri, Proxima Centauri sits or lie about 4.3 light years away. So just over 4 years. We would all be 4 years older, makes sense. The people on the spacecraft, when they got there, would only have aged by 65 days. Yeah, that also starts bringing in all those paradoxes with twins, with going back to kill your grandfather so that you're... But they are just paradoxes, because it basically means that you wouldn't be here. If you had to go back and change anything, you wouldn't be here. Unless, of course, we're in a parallel universe. We're not going to go down that road. As far as we know, parallel universes don't exist. So going back in time to change something would basically ultimately change what happens here and now. And that is there's a Israeli physicist in Haifa that is working on basically a donut-shaped wormhole, and his big thing there is that you can't change anything that you've created that has been created before the wormhole. You can only change things after. So you can't go back in time. You can't travel back in time and change things. But yeah, I was going to do a couple of videos for you, but I thought trying to explain it and using my arms as Greeks do might be better. There's lots of different videos explaining time dilation, but also explaining space travel at those speeds. You can Google that, you can get lots of information. But I wasn't going to sit here and let you watch videos. I thought I'd just put something together much better all round. That's a quote from, again, Carl Sagan, my hero. No, my hero. And it's basically, for me to actually add to that, very, very difficult, except basically it's what we do and what everybody can do right here and now, how we can change things. I mean, we're talking about going to Mars. I mean, I don't know what's going to happen in 40, 50, 60 years' time and how we're going to change that planet, how we're going to affect the outcome of a Martian thing that will certainly be totally different once humans get there. We're going to mess it up. Stronger words than mess it up. I firmly believe we are. Look what we're doing to this Earth. I said earlier on that Starlink satellites, I haven't got much time for Elon Musk and his satellites. I firmly believe that there will be a time where future generations will not be able to see any stars. And how sad is that? I mean, we evolved thousands of years ago, millions of years ago. We sat down and we spoke over the fire and we looked up and we saw stars. And I genuinely believe that with Starlink and the rest, I mean, that's just one company, with the rest of the people getting on board, future generations will sit outside and will not know what our night skies look like. I mean, at the moment I can see it with my astrophotography, certain times of the evening, certain times in the early mornings. If you wanted to do any science with those photos, it's impossible. So yeah, it's what we do here and now. Even picking up that piece of plastic or when you're walking on the beach, it certainly helps. It certainly does. Thank you. I hope I didn't bore you. And I'm sure there's going to be lots of questions. So if you want to ask, please go ahead. And no alien questions, please. Are there aliens out there now? Yes, Jason.
I just want to mess with your head, man.
Zeros. You want me to get the zeros up?
So I've heard that the universe is expanding faster than the speed of light. In other words, if you're observing distant galaxies, they will be unobservable in a period of time. So they are moving faster than the speed of light. Presumably, they have some matter. So that sort of counters the argument that there are only protons that can move faster than the speed of light.
Okay, so don't forget, as Newton, as all your great scientists work things out, I'm sure we'll solve that. Somebody will come along and change Einstein's theory of relativity, his general relativity. But at the moment, I've got no answer for that. I didn't even touch on travel past the speed of light and what happens to communication, because then how are we going to communicate if sound waves can only reach the speed of light and we are traveling 5-10 times faster than the speed of light? How are we going to communicate? It throws another angle. So I don't know. I mean, I can't answer that question for you.
After
Starlink. It's okay. So basically, it's Elon Musk initiative. His original idea was to give internet to the masses that couldn't afford it. He was driven basically by government, US government and military, to provide the forces and the government with reliable internet connection. So I think that's what basically paved the way for Starlink. But now, I mean, it's open season. I can go buy a satellite. I can buy the hardware, 15,000 rand, and then pay the same amount that I'm paying to Computer Hut and get absolutely fantastic speeds. I refuse to do that. I'll sit with Computer Hut and just use. To me, it makes no difference whether I've got slightly faster speeds or more bandwidth or whatever. Yeah.
So do you mean that so many satellites are going to...
So what happens is, to cover that footprint, you need not just one, you need thousands. So yeah, millions. And that's basically what's going to affect, yeah.
I think I'm correctly saying Isaac Asimov first used the term parsec in the 1950s or 40s when he was writing the science fiction book. But what does a parsec measure? How far is a parsec in terms of speed?
Parsec's quite interesting actually, and you can try this. Just put your arm out and hold your finger up and find something find an object to point at, and then close your one eye, open the other eye. You see that movement? That's called, parsec actually means parallel second. So that distance that you're seeing in that movement, the apparent movement, is the distance between your two eyes. And knowing that distance and the fact that there's a right angle here, my nose is, with basic trick you can work out angles and distances to that light. That is how we first used, when I say we, that's how astronomers first utilized the parallax method to determine distances to stars. So it's about 3.2, you'll have to Google it just to check, of a light year, yeah. 3.26, there we go, yeah. Yes, that's correct, yeah. Yeah, I do know that, yeah. The first determination. Also the first time that we realized that Alpha Centauri had a third companion, which was closer than about the two stars, Alpha and Beta Centauri, was Robert Arns from South Africa, from SAO, and he discovered Proxima Centauri. So the South African astronomy heritage is actually quite rich, because we've got good skies. Yeah. Okay, so yes, I was going to add to that worm. 5 minutes.
People are struggling to hear the questions.
Okay. Sorry, can you repeat that?
The question which I'm asking is that if you look at Einstein's theory, E equals mc squared, the sooner you get to the speed of light, your body will increase in weight. Anybody will increase in weight. You showed us on one of your slides as to how the joules escalated as you got to the speed of light. Now, the question is, if man wants to travel out into space, he has to exceed the speed of light. And you were talking earlier on about wormholes. Now, I don't quite know. There is research work at the moment with things like the Hadron Collider in Switzerland, which they are trying to establish something like this, and they have actually found that certain particles which they've accelerated to almost the speed of light disappear. But once that glider comes down in speed, the particles reappear. Is there a possibility that man will be able to at some stage exceed the speed of light?
Yes, there is. Yes, there is. So to travel at the speed of light or close to the speed of light or past the speed of light at the moment is impossible. We can't do it, which is understandable. The energy and the energy that is required to move that mass just gets higher and higher and higher to a point where it can't happen. So the other way of doing it is with gravity. That's another way of basically bending space-time, where, as I mentioned earlier, you create a wormhole, a donut-shaped wormhole. There's a scientist in Israel who's actually working on that. The problem there is very similar to exceeding or getting close to the speed of light. To create those levels of gravity required to change space-time, again, you're looking at super massive black holes that we cannot generate that amount of energy to shape space-time. Maybe there will be a time where we can, and that will allow us to bridge that gap and basically be able to travel through vast distances. But at the moment, no, we haven't got the means of changing that gravitational attraction to a point where we can change space-time.
Okay, just wait for the mic, please.
Are you the mic?
Mic.
Key to understanding why wormholes work. Key to understanding why wormholes work is that instead of trying to exceed the speed of light, you're changing the fabric of space-time itself. So remember, you can only travel slower than the speed of light in the space-time where you are. But if you start changing space-time itself, the rules change. That's the simplest way I can think of it.
Yeah, that's. When you have light passing through, passing close to a star, for argument's sakes, that light, that star's gravity will make that light bend, okay? Which is basically trying to visualize that space, that bent in space, but it's not quite what I'm trying to get at. If you wanted to bend the space-time around that star, the amount of energy that you would require would be it's astronomical. There's no ways we can even think about doing it, and that would allow you to bridge that gap. But as you said, it'll just create other different problems. I mean, traveling faster than the speed of light. Just the comm side would be how would you wrap your head around that? You'd be talking. I mean, we can send robots, and we have, to Mars, to Venus, to within a few million kilometers of the sun, robotically. We can control them from the Earth. What happens now if something's fast that receives a signal or can't send it? I mean, so it would receive a signal before it could actually, it will already be there. And the signal is still trying to get to, tell it to change course, or, so. I mean, it's pretty much the same on a smaller scale. If in 10 years' time we manage to travel at 50% or 10% of the speed of light, and in 51 years or 55 years' time, somebody worked out they could travel at 100% the speed of light or 99%, and we go to Alpha Centauri, they would get there before somebody who left prior, build a house and whatever, a whole community, and then we'd get there saying, what the heck? Where did you come from? Go for it.
You want to just tell the people
He doesn't need a
what
mic.
is it that you have there on your farm in those little houses, because that was fascinating to me.
It's a secret, Wilfred. So I'm fortunate I have the use of an observatory that a client basically pulled out of. But what we essentially do from an astronomy point of view is Sarah and I host 5 observatories, one at Purley, one in Bonnievale, one in Springbok, and 2 up north, All Days and Limpopo. And they basically are utilized by an American company that looks and tracks for satellites. So there's conflict of interest there for me, because I presume at some point they're going to be looking at Musk's stuff, which is not going to bode very well with me. But so they look at satellites, they track satellites. If you remember, a couple of years ago, a Russian satellite collided with another one, or a European satellite, and there was a big hoo-ha. They actually captured that. They saw it coming. They tried to warn, or they did warn people. So they do that, and they also look for NEOs, near-Earth objects, especially close to the sun, because our Earth-based telescopes and our space-based telescopes can't pick that stuff up. So that's actually quite a cool, that's very, very cool science that they're doing, because those NEOs could potentially be Earth-destroying. So they do that as well. And all I do is I make sure that I sweep the floor, make sure the cables are all tidy, etc., etc. If there's any issues, I'll try to sort them out. But as I said, the one observatory I utilize, I've got a couple of telescopes in there, and when the weather allows, I spend a lot of time in there. I wish I could put a bed and a fridge and an oven in there.
So, Sarah,
She gets an invite every night and she declines. Thanks, guys. Thank you for your time. I hope you enjoyed it.
Thank you officially.
Oh. Thank you.
so much.
Can I give it away?
Well, this one.
There you go.
Give it back to me.
Thanks.
Thank you so much, Kos. Thanks for sharing your interest, and I think that was very interesting. I think all of you did. If you guys want to listen to this again, because it was everything and anything you had to listen to understand, it will be on YouTube if you want to go and watch it again. And if you have more questions, Kos will be around afterwards as well. I just quickly wanted to do a little marketing talk. It won't take too long. I just wanted to share with you that our marketing team has been very busy at the start of the year. One of our marketers has been to ITB in Germany, in Berlin, to market Transpy, and we are also planning to go to World Travel Market Africa in Cape Town in April. And then we also have a few other tours coming up in the rest of the year, but I will share that a bit later. Then I want to thank you guys again for supporting these evenings. Again, the contribution that you guys pay for to be able to attend goes towards the Conservation Trust. And we also want to re-invite you and also motivate you to send us visitors to the Penguin Sanctuary. Penguins always appreciate it, as well as our team. And then I know everyone's hungry, so I want to thank the Great White House and Marine Dynamics for sponsoring tonight. And also I want to invite you guys to please stay afterwards and enjoy some soup and bread made by our chef Pete and his team in the kitchen. And I hope you enjoy the rest of the evening. I will send out invites for our next evening in April, and this is an important notification. We had some security, not issues, but some of you might wonder why you're not receiving the invites anymore. The reason for that is we had to double down on the way we send out our invitations through bulk email. That's usually through something called MailChimp or the program that we're using. So there has been some security changes, and we had to resubscribe most of the emails, and a few of yours probably don't allow you to receive bulk emails. And for that reason, if you know that you have received previously and not receiving anymore, please ask us for a resubscribe link so that we can make sure that you can get back on that list when we send out the invites. Otherwise, keep an eye on Facebook and on the local Hanspanlaker. We usually share the details there. Alright guys, again, thanks for everything. Thanks for listening.